Okay, I guess it is recording. So, okay, you can go ahead.
Okay. All right. Yeah, so thanks for having me. So today I'll talk about joint work with Eric about forecasting algorithms. So, okay, well, I guess I'll start with kind of the problem that motivated us for this project. This is the problem of composition and query complexity. So the setting is you have a Boolean function f from strings of length n to 0, 1, and we're interested in the worst case number of queries that are required to compute f. So this means kind of the minimum number of bits of the input you need to read before you know the value of f of x. So we're thinking of like an adaptive model where you can read the bits of x one at a time, and the only cost is the number of bits that were read. Particularly, we're interested in randomized algorithms. So these are algorithms that are allowed to make decisions randomly. They must succeed in the worst case over inputs, and they're allowed to make error. The error is against the internal randomness of the algorithm. It's kind of the usual setting. Kind of a VPP style measure. Okay, and in particular, suppose we have actually two such functions, f and g. We can look at the composition of f with g, and by that we actually mean the block composition. So think of something like this, this figure on the right, where you have n copies of g, one for each bit in the input to f. And the input to the composed function is this long string of length n times m that represents n different inputs to g, to different copies of g. And then the final output of the function is the output of evaluating all the functions g and then evaluating f on the result. So, okay, this is kind of a natural object. It's kind of, we create I guess a formula out of these f and g's. And then the question is, what is the randomized query complexity of this composed function? So that is, compared to the randomized query complexity of f and the randomized query complexity of g. And one thing you can hopefully see is that we know that the query complexity of f composed g will at most be the query complexity of f times the query complexity of g, well, up to log factors. And the reason is, suppose you knew an algorithm for f that only reads a few bits, and you knew an algorithm for g that only reads a few bits. Then you could run the algorithm for f, and every time you needed an input bit to f, you would call as a subroutine the algorithm for g to compute that copy of g. And that just works. The only subtlety is that these are bounded error algorithms, so your algorithm for g may fail with some small probability, and you're going to have to union bound, so you're going to have to make that probability of failure pretty small, and that just requires amplifying. So it requires repeating g, running g, that one copy of g, several times independently and taking a majority vote to reduce the error to a level low enough that even all the errors together, kind of the union bounding over all the copies of g, won't be more than a small constant. And that's just a kind of a log factor overhead. We'll ignore it, and we'll say that the randomized query complexity of f composed g is at most the randomized query complexity of f times the randomized query complexity of g. Okay, and the main question, the composition question in query complexity is R of f composed g at least R of f times R of g up to constant factors? So does is this the best possible strategy regardless of the functions f and g, or is there some f and g for which you can substantially improve on this? So you can imagine one infinite family of f's and another infinite family of g's, such that whenever you compose them together, somehow there's a faster algorithm for computing the composed function than this trivial one, asymptotically faster. Okay, so this is the question. This is kind of it's an embarrassingly simple question, I guess. It's you know, it's one of the first things you might ask in this model. Analogous questions for deterministic query complexity. This is known for a long time. For quantum query complexity, surprisingly, it's also known for a long time. So this theorem holds both for deterministic and quantum query complexities. But for randomized, it's been open. It's kind of this frustrating open problem. Okay, but before we get to this problem, let's kind of step back and ask kind of why are we doing this? This is a question I sometimes get.
So any previous lower bound?
Sorry?
Any lower bound for randomized complexity?
Right. So of course this is kind of a very general function of general f and general g. There's several previous works that have, for example, said R of f composed g is at least R of f times some measure of g. There was one recently that says is at least R of f times square root of R of g.
Okay.
That's one thing we know. There's some measures, some results that say R of f composed g is at least some measure of f times R of g, although those are a bit weaker. We don't know whether R of f composed g is at least square root of R of f times R of g. Kind of we have better control over dependence of g than dependence of f on f. And also, there's yet more previous work that kind of defines lower bounds for randomized query complexity that themselves compose. So for particular f and g's, maybe using this lower bound technique is good enough, because once you show a lower bound for f and a lower bound for g using this specific technique, you're guaranteed that it will work for the composition too. One such technique actually is quantum query complexity, because we know quantum query complexity composes, but it's not the only one. This is kind of a question only up to polynomial factors. So we do know kind of that it's at least R of f times square root RD. But yeah, it's we worry here about polynomial factors and not like logarithmic factors. Say that this is basically the best that's previously known. Okay, and any other questions about this? Okay, so yeah, as I was saying, stepping back a bit, why worry about this question? I mean, okay, maybe it's kind of a nice, elegant question, but why are we doing this? And I get this question sometimes from colleagues, who say, why do you study query complexity? What's the point of it? Query complexity is not real life. It's kind of the model is it's so simple that it sounds almost irrelevant. Yeah, of course, this is a little bit of a mean question, but I respond with, well, at least we can prove things. By which I mean that we know that in regular complexity theory, it's very difficult to prove the non-existence of a fast algorithm for something. Proving that there are no fast algorithms is a very difficult task in general. In query complexity, on the other hand, in query complexity, you can prove the non-existence of 3 different algorithms in the shower each morning. Or okay, maybe that's a bit of an exaggeration. I mean, now with the COVID-19 situation, nobody showers every morning. Okay, but it's still it's much easier to prove lower bounds in query complexity than kind of in real life, where by real life you mean actual complexity classes, like BPP or P. Okay. Well, I get this response. Who cares if you can prove things? It's still not real life. Okay, I mean, okay, this is kind of a sad perspective. I think, you know, the right solution to this is to say, okay, maybe it's not real life, but it's a useful model. By studying query complexity, maybe we can learn something about real life, about true algorithms by studying this kind of toy baby model of algorithms where things are supposed to be much easier. And this, I think, is, you know, it's also why the answer you might give to why study theory at all. Of course, theory is not quite real practical algorithms, but we hope that it's a useful model for practical algorithms. But actually, the conversation is not over, because this actually raises a new objection, which is, you know, maybe this is true for some obscure complexity measures where we don't have good intuition for them. We need oracle separations. When is the last time randomized query complexity gave a new insight about randomized algorithms? You know, if we're talking about the composition question, presumably we're trying to learn something about randomized algorithms. Is there really any hope of that? You know, don't we know a lot about randomized algorithms already? So what I want to claim for this work, the main point of my talk here, is not going to be about the original composition question in query complexity, but actually I want to claim that yes, studying it taught us something new about randomized algorithms in other models as well. And I care more about this insight that was gained than about the original composition question. So kind of let's abandon this original composition question and only talk directly about what I think studying it has taught us about randomized algorithms in real life, where, you know, by real life I kind of mean not the query complexity setting, still theory, but you know, not specifically this model where you only count the number of queries. Okay, so
your
what
colleague
is this?
shy?
Sorry?
Is your colleague shy?
Sorry?
A colleague that you are mentioning, is it shy?
No, my colleague is Eric Blake.
Okay.
Yeah. Yeah, he, yeah, so this is, I guess I don't know if I mentioned, this is joint work with Eric Blake. So he was on the first slide as well. So this was all stuff we've done over the last year.
No, but I would like to refute. I never said any of those questions you have on this present slide.
Oh, this colleague. Oh, I see. Oh, the one who's asking me all these questions. Oh, I see. Yeah. Oh, no, I mean, this is oh, sorry, I misunderstood. Right. Yeah. No, this is kind of, yeah, I'm just, well, maybe I don't have a specific colleague to name. This is kind of maybe nobody is quite this explicit about it. People only hint it, and I imagine this is what they think. So yeah, I mean, maybe, you know, maybe people are truly more polite in their head than the story suggests. But, okay, this is kind of what I imagine people think when I talk about query complexity. Okay, so let's in any case, let's go to this insight that I claim that we have. So the insight is, okay, I'll state it like this. So the insight is this: suppose you are dealing with randomized algorithms in the small bias regime. So I mean, bias, say 1 over polynomial in the runtime, not like inverse exponential, but, or yeah, maybe not 1 over x in the runtime, but 1 over poly in the runtime. And in addition, you want to do a fine-grained analysis. So you care about polynomial factors. You care about polynomial factors in both the runtime and the bias. Then consider switching from talking about, from talking about the bias of the best randomized algorithm to talking about the score of the best forecasting algorithm. You know, I'll explain what this means. So, you know, just a little bit more about the setting where I claim this will be relevant. randomized algorithms, okay, we deal with those pretty regularly. Small bias regime, maybe one to kind of give a hint on the motivation of this. In cryptography, this is usually the regime you care about. Usually you care about not succeeding even with polynomial bias. So this kind of a function that's negligible is exactly a function that's not one over poly. So on the other hand, in cryptography, usually people do not care about a fine-grained analysis. So this is kind of the setting. Suppose you were in the small bias regime, but you happen to care about a fine-grained analysis after all. So you care about these polynomial factors in the bias. Okay, this is maybe a bit less common of a situation, and maybe this is why this insight has not, to our knowledge, been previously previously introduced or previously seen. So, but I do kind of want to try to convince you that if ever you are in this setting, then this is the right thing to do. The score of a forecasting algorithm, which we'll define shortly, is a better measure, a better way to get a handle on what is this randomized algorithm doing, how much bias does it succeed in achieving. Okay, so let's talk about what these forecasting algorithms are and what the score is. Okay, so this all starts with the idea of scoring rules. And scoring rules are the answer to the following question. Suppose you're paying someone to make a prediction. How should you reward them? So for example, somebody, the predictor, you would like to incentivize them to give you good predictions. They're saying 70% chance of rain tomorrow. Okay. What should you do if your goal is to, have them tell the truth? So, you could reward them if they're right, which means, say reward them if it rains. Of course, then you're ignoring the chance. They'll just say it rains if they believe the probability of rain is above 50%. I mean, I assume they think in probabilities here, just for simplicity. So, assuming they kind of have a Bayesian view of the world, they have kind of a probability they believe to be the true probability of rain. If we pay them on a correct prediction, they'll just predict it will rain if they think the probability is above 50%. This does not distinguish 100% chance from 51% chance. You could give them 70% of their reward if it rains. But a bit of thought reveals that this is the wrong thing to do. Actually, it incentivizes them to say 100% chance of rain if they believe there's a 51% chance of rain, because they want to get all the reward in case they're right. So, or at least they would be indifferent between these choices. So this is still not aligning their incentives right. And more generally, if they predict the chance of rain is P, what should the reward be if it rains, and what should the reward be if it doesn't rain? And a scoring rule is just going to be some reward function. So just some function from 0, 1 to R, such that we give reward S of P if it rains and S of 1 minus P if it doesn't rain. So this is just a scoring rule is really just a function from 0, 1 to the reals. Okay, and we interpret in this way. We interpret as the reward we pay someone, and we can pay negative reward, which means we charge money for a wrong answer, say. Okay, now proper scoring rules. So we say a scoring rule is proper if it incentivizes a Bayesian predictor to give her true subjective probability. So this is kind of a, imagine that the predictor, let's call her Alice. So imagine that she's Bayesian. She has some true probability that she assigns to the event of whether it will rain tomorrow. And our goal is to incentivize her to tell us the truth about her belief. So suppose that Alice believes that the true chance of rain is P, and she outputs prediction Q for whether it will rain. So, she believes her expected reward to be P times S of Q plus 1 minus P times S of 1 minus Q. Why? Because, you know, her reward will depend on Q with what she tells us. But, you know, her belief, the reward will also depend on whether it rains or not. And her belief about whether it rains or not is, you know, that there is P chance of raining. So from her perspective, her expected reward is P for whether it will rain times S of Q for the reward in case it does rain, plus 1 minus P, the probability it doesn't rain, times S of 1 minus Q, the reward for when it doesn't rain. Okay. And we want this to be uniquely maximized at Q equals P. So this would incentivize her to only say the, you know, her true subjective probability as the probability she reports. Okay, so this is what we want, the property that this function is uniquely maximized at Q equals P. This will incentivize Alice to say 70% of rain, 70% chance of rain if she believes there's a 70% chance of rain. So more formally, we're just going to call a squaring rule proper if for every fixed P, the expression P times S of Q plus 1 minus P times S of 1 minus Q as a function of Q has unique maximum at Q equals P. Okay. Okay, that's relatively straightforward. So let's just show an example of a proper scoring rule. So one proper scoring rule is a log score. So the score will be just the log of the probability. You know, this is sort of has an interpretation, which is the forecaster pays an amount proportional to the surprisal in the information theoretic sense. This is kind of the log of 1 over the probability assigned to an event is kind of how much you're surprised by the event. And here, I mean, the log of a number less than 1 will always be negative. So here we're thinking of Alice is always paying us depending on how wrong she was. So in particular, she pays log of 1 over 0.7 if she predicts it will rain with 70% probability, and it indeed does rain. And otherwise, she pays log of 1 over 0.3 if it doesn't rain. It turns out that Alice is incentivized to give her true estimate in this case. It's not too hard to show using just elementary calculus. You know, it may be a bit weird to say that she has to pay us kind of an arbitrary amount. What if we want to pay Alice instead? Well, of course, okay, this means that S of Q should be positive. And of course, we can always scale S of Q by multiplying it by some positive constant and adding another positive constant. And this doesn't change whether the scoring rule is proper or not. So we can kind of shift and slide S around without changing whether you know, whether it's proper. Which in particular means that we could just say, okay, Alice pays. Normally, Alice would pay log of 1 over the probability assigned, but here we can say that in any case we will give her first $100 before this game happens. So she agrees to play. The only problem is that log of 0 is negative infinity. So you know, if she assigns probability that's close to 0 or 0 to something, and then it happens, then the amount she owes us is arbitrarily close to infinity, or literally infinity in the case that she actually says something with 100% confidence and ends up being false. So there's no amount of money we can pay her in advance to incentivize her to play this game necessarily. Or I mean, well, okay, I mean, at least there's no amount that makes it so that she can always actually pay back without you know, going bankrupt. So this is a bit of a problem. So there's actually another scoring rule called the Breer score, which is, it's also very simple. It's -1 minus q squared. And the Brier score, first of all, it's also proper. And after a bit of shifting, it's bounded as well. You can make it positive and bounded in 0, 1. And suddenly, this is exactly what we wanted. This means that, we can now just pay Alice S of q, and it's always us paying her, based on to what extent her prediction was correct, and her incentives are now aligned. And this was proposed in 1950 for exactly this question of incentivizing weather prediction. So this is how you should pay, the weathermen should be based on the correctness of their predictions in this way, so that they try to get it right, or at least so that they don't lie about what they think the weather will be, I suppose. Okay. It turns out there's actually many other scoring rules. So it's a bit surprising at first that it's not just one such function. There's just a ton of them. It's just like, you pick a function out of a hat, and it turns out that it happens to be a proper scoring rule. It's I was surprised by just how many of these there are. Okay, so they're apparently nothing particularly special. There's a lot of such rules, but if you don't aim to find one, then you'll pick a reward function which is not proper. So it's good to at least know of this concept, so you can check whether the reward you want to give is correctly incentivizing or not. Okay. In this work, we're going to care about a special scoring rule. This one, 1 minus square root of 1 minus q over q. We've normalized it so that S of 1 is 1. So if you kind of make a perfect prediction with 100% confidence, the reward is 1. And giving a 50-50 prediction is reward is 0. Giving a wrong prediction will be a negative reward. An incorrect prediction loses points here, and this scoring rule is not bounded. Actually, it does go to negative infinity on a sufficiently confident wrong prediction. This one is a bit more obscure. We had a hard time finding it in the literature at all at the beginning. It turns out it does previously appear in the literature under the name boosting loss, which I don't fully understand the connection to boosting. Apparently there is one. And it has the magical property of being amplifiable, which we'll see in a minute. So this is from now on, when I say score, I mean with this one scoring rule. Okay, so although there's many proper scoring rules, this one proper scoring rule is the best for our purposes.
So Shalev, this like amplifiable property is the main thing that you're going to use, and I guess you'll explain what that means in a bit.
Yeah, that's the main property, although there's a few other simpler properties that are also relevant. But yeah, amplifiability is the one that we can't establish for anything else. Yeah.
Okay, and this is rather asymmetric in the sense it goes from like 1 to 0 when you're at 50-50, and then minus infinity for like a 0 prediction.
Correct. So if you predict with 0% confidence, and it happens, and the event happens, which you said 0%, then yeah, the reward is negative infinity, and it diverges to negative infinity really fast, actually. Yeah, and at a half it's 0, and at 1 it's 1. Yeah. Okay. So and of course, so note that it's only asymmetric between getting it right and wrong, not between answering 0 and 1, right? So there is still a symmetry because we reward based on either S of q or S of 1 minus q. There's still a symmetry between predicting yes and predicting no. Like those are still symmetric. It's only getting prediction right versus getting prediction wrong. That's asymmetric. Okay, so right, and let's talk about forecasting algorithms. What are forecasting algorithms? A forecasting algorithm is just a randomized algorithm that outputs a value in 0, 1, the interval, rather than 0, 1, the set. So it's a randomized algorithm that outputs a probability rather than outputting, a yes, no answer. And we interpret this probability as being the confidence of the algorithm's belief that the answer is 1. Okay, so the algorithm runs, does whatever it wants to the input, and then gives you a confidence of whether it thinks this input is a 1 input. Now, the score of a forecasting algorithm is going to be the worst case expected score. This means worst case over inputs x of the expectation over the internal randomness of R of the score of the output of R with respect to the right answer f of x. So remember, the score always depends on the right answer. That tells you whether you're taking s of q or s of 1 minus q. So here, the right answer will be the true value of f of x, where x is the input. And so, this will, once we know the true answer, we know how to take a number in the interval 0, 1 and convert it into a real score from the function on the previous slide. And then we take the expectation over this value over the internal randomness of R, okay? But we don't posit any distribution over the inputs. This is still worst case over the inputs. And note that there's no longer any interpretation of the form incentivize a Bayesian agent. There's no notion of what does the algorithm truly believe, because the input is worst case. So a belief usually, well, a Bayesian belief needs a prior. So if you are Bayesian and you're running this algorithm and you're updating your belief about what you think x is, whether it's a 1 or 0 input, to do this Bayesian task of you need a prior distribution over the inputs x. And here we don't have a prior distribution. We're taking the worst case over inputs x. So it's fundamentally a non-Bayesian setting, one more analogous to the usual notion of worst case complexity. But even though there's no longer such an interpretation, we still can define this worst case expected score, and this is what we do. So we just assert this definition that this is the score of a forecasting algorithm. Right, this is just what I was saying. Okay, the only randomness here in this expectation is the internal randomness of R, no expectation over the inputs x. Okay, so let's just do a brief example from query complexity to see the difference between evaluating a randomized algorithm kind of in this forecasting setting versus in the worst case setting. And particularly, we want to compare it to a small bias randomized algorithm. So, okay, consider two types of small bias randomized tasks. The first task is to distinguish the Hamming levels n minus root n over 2 and n plus root n over 2 using a single query. So, these are the Hamming, it's Hamming levels near the middle, near n over 2, but separated by plus or minus root n, effectively. Okay. And we have one query to the input. You're allowed to read exactly one bit of the input string. Okay, so you're given a string which is either Hamming weight, either it's half ones plus root n ones, or it's half ones minus root n ones, and the rest are zeros. And the string is of length n. And the goal is to read exactly one bit and to say which it is, whether what is the majority of the string, essentially. Is it more ones or more zeros? And we can achieve bias root n for this task just by querying a bit at random and then outputting this bit. And it's not too hard to see that the bias, you succeed with probability close to a half, but the bias over a half is 1 over root n, or in the order of 1 over root n. So, okay, this is task number 1. The second task is to distinguish Hamming levels 0 and root n using one query. So very similar to before, still a one query, still an input string of length n. But now the task is to distinguish Hamming levels 0 and root n, so either no ones or root n ones out of n positions. So it's going to be mostly zeros either way. And here we can also achieve bias roughly root n by picking a bit at random Of course, this time a bit of random will be almost always 0, so we don't want to just output this bit, but we want to say, okay, if we see a 0, then say 0 with probability close to 1/2, and if you see a 1, say 1 with probability 1. So you can fine tune these parameters such that you get kind of this symmetric bias situation where in the 0 case you accept with probability, or you say 1 with probability slightly less than 1/2, and in the 1 case you say 1 with probability slightly more than 1/2, and the gap there is about 1/√n again. Okay, so these look like similar tasks, but despite appearing equally difficult, these tasks are quite different, because in the second one you find a certificate with small probability. So if you find a 1, you know for sure what the string is. You found a proof. And in particular, you can amplify this with root-n repetitions of the algorithm. So just repeat this algorithm of query 1 bit at random, and query now root-n bits at random, each one independently of the rest. And that's good enough to get bounded there. But in the first task, amplification requires n repetitions. And just measuring the bias doesn't tell you which situation you're in. So just saying, oh, the bias we can achieve for this task is 1/√n, it failed to distinguish which type of 1/√n is it. Is it the 1/√n type similar to the first case where you know nothing except for a slight bias? Or is it the second case where probably you saw nothing, but you had a small chance of just completely solving the problem? These are kind of very different scenarios that both give rise to the same small bias. And I would argue that measuring these in terms of bias gives you a bit of a misleading picture of the difficulty of this task. I mean, yes, it is true that this is the best achievable bias, but it doesn't tell you much more than that this is the best achievable bias. Doesn't tell you how much it would take to amplify, for example. Interestingly, if you look at the difficulty of this task in terms of the worst case expected score, using the scoring rule mentioned previously, then the best you can achieve for the first task is 1/n, and for the second task it's 1/√n. So suddenly you can see the difference between the difficulties of these tasks, and this is because the algorithm now has the freedom to tell you, yeah, I think it's a 1 input, but I'm not sure. And in the second case, it will say, okay, now I'm 100% sure that it is really a 1 input like I thought. And allowing the algorithm to give you its confidence, even though this is a worst case task, even though there's no distribution of the inputs, so that the algorithm can't possibly be Bayesian, still this is useful to allow the algorithm to tell you this information. Even one query algorithm, then suddenly you can see the difference between this model and the bias model and why this is more informative. Okay, so this is the concept of a forecasting randomized algorithm. Now I'll talk about the amplification property that we needed. And this property only happens with the special scoring rule, and it says that the worst case score of a forecasting algorithm, this is the worst case expected score as before, it's amplifiable. This means for this one scoring rule, suppose you have a fixed input x and you have an algorithm, forecasting algorithm. So you want to increase your confidence or in the value of the input. So you want to kind of run the algorithm several times, each time with independent internal randomness, and you get several different predictive outputs, right? So you get different confidences. Say 0.6, 0.9, 0.8, 0.3. These are kind of the confidence that the algorithm tells you about the value of f of x in each independent run. And it turns out there's a way to combine these outputs, well, effectively by multiplying the corresponding odds ratios associated with these predictions, which would be the Bayesian thing to do if you were Bayesian after all. When you combine these outputs in that way, then in this case you get the confidence 0.96. But the key point is the following guarantee. The guarantee is if you combine the outputs in this way, then the expected score of the new algorithm on the one input x is exactly 1 minus s to the k, where k is the number of repetitions of the algorithm, and s is the expected score of a single run. Okay, so what happened? So we had expected score s for a single run. Maybe this was small. Now what we want is to, run it multiple times. We get all these confidences. We have a way of mixing them together into one confidence. And the guarantee is that the expected score of this new algorithm, expected over all the independent internal randomnesses of all these runs, it's going to be exactly 1 minus s to the k. And this function, 1 minus s to the k, is roughly k times s. Okay, so you have precise control over how your score will improve as you repeat the algorithm. Okay, this is actually a significantly better amplification than the bias of randomized algorithm, where there's no closed form for that one. Okay, so this is kind of the key magical property, but another very useful property of this one scoring function we picked is that you can go from bias to score and back. So in particular, if you have a regular randomized algorithm which achieves bias gamma, then you can convert it to a forecasting algorithm where the expected score, the worst case expected score, is at least gamma squared over 2. And the conversion is simply, okay, run your normal algorithm R. If it outputs 1, then just decrease the confidence from 1 to 1 plus gamma over 2, where gamma was the bias. And if it outputs 0, then decrease the confidence to 1 minus gamma over 2. Okay, and that's it. Just evaluate based on that, and already you're guaranteed that the expected score of this will be at least gamma squared over 2, where gamma was the bias. You didn't note you didn't need to modify the algorithm at all. You only kind of do modification to the output of the algorithm. Okay, so no difference in the query structure, or no difference in what the algorithm did internally, except for what it outputted at the end. You process that only. And in the other direction, a forecasting algorithm with expected score S can be converted into a regular algorithm with bias at least S. Okay, how do you do that? This is again very simple. You run your forecasting algorithm. It's going to give you some confidence in 0, 1, the interval. And what you will do is you will output 1 with probability Q and 0 otherwise with probability 1 minus Q. So you just take this confidence in 0, 1, treat it as a probability, and take a Bernoulli sample with that parameter. Okay, and this turns out to give you bias that's at least the score of the forecasting algorithm you had. Okay, so these both hold with respect to the one magic scoring rule. The other scoring rules actually don't necessarily satisfy this, depending on which one you go with. Okay, this means the best achievable bias is within a quadratic factor of the best achievable score, because it can convert back and forth. This is true basically in any model of computation, because this conversion is so simple in both directions that any model can do it, pretty much. Okay, and it also means that the bias and score are just effectively equivalent in the constant error regime, because then we don't care about differences of only a constant in the constant error parameter. When the bias is a constant, and the score will be a constant. Okay, and the point I want to emphasize here is that the score can be thought of as a more fine-grained way of measuring success than the bias. As we saw previous with the example, the score gives you more information about success than the bias does. Okay, because it allows you to say whether you're certain or not. It allows the algorithm to give a confidence. Okay, and so returning to the main insight, this is the same slide we had before. Suppose you are dealing with randomized algorithms in the small bias regime, and you want to do a fine-grained analysis. Then I posit, you should consider switching from talking about the bias of the best randomized algorithm to talking about the score of the best forecasting algorithm for your problem. Under, I would recommend that particular proper scoring rule. That's the one that worked for us, that we've analyzed. Okay, any questions so far? I guess we're running a slightly low on time, but that's okay. Okay, any questions so far about kind of the main message? Okay, if not, then let me briefly talk about our application of this, or where it came up for us. Where it came up is in minimax theorems. Let me just briefly talk about Yau's minimax theorem, introduced by Yau in 1977. It says the minimax principle or minimax theorem applies in concrete computational models like query complexity or communication complexity, where the input set is finite. And it basically says the following: for any function f, there is a hard distribution mu over the inputs, such that computing f against mu is as hard as computing f is in the worst case. So there's always some distribution such that average case against this distribution is as hard as worst case. And this is maybe surprising when you first see it, but it's an extremely useful property. So I'm sure many of you have already seen it. So it's particularly useful for lower bounds, and it kind of says that there is a tight low bound technique for randomized algorithm, which is providing this hard distribution, and it always must exist. The hard distribution against which all randomized algorithms will fail. It even suffices to show all deterministic algorithms that are too fast will fail, because a randomized algorithm is just a convex combination of deterministic ones. Okay, and what we cared about in this work was the following generalization. So first of all, Yau's minimax also works for small bias algorithms. It says basically, suppose T was the worst case cost of computing F to bias gamma, then there's a hard distribution mu such that any algorithm achieving bias mu bias gamma against inputs from mu must have cost at least T. So again, this is kind of saying there is a distribution mu such that average case against mu is as hard as worst case. So here's the problem, or the problem we had, is that this hard distribution mu depends on the bias level gamma. For different bias levels, in general, the hard distribution will be different. And this is sort of a fundamental issue with the way Yau's minimax is proven. There's actually very few guarantees on this distribution mu. It might not even put equal probability mass on the 0 and 1 inputs, which is kind of a ridiculous thing to do for a hard distribution. But this can certainly happen. You have no control over what mu will be. It's kind of a non-constructive proof of existence. The distribution mu, although we know it's hard to solve to bias gamma, maybe it's trivial to solve to a bias smaller than gamma, right? So it's hard for this bias level. Maybe it's completely trivial for a slightly smaller bias level. The question we were worried about is there a distribution that certifies the hardness of F against all bias levels at once? And, at first one might wish for a statement like this: for all F, there exists a mu such that for all gamma, the average case cost of computing F against mu to bias gamma, this is the R superscript mu subscript gamma, is at least the worst case R subscript gamma of F. So the worst case cost of computing R to bias gamma. Unfortunately, this turns out to actually be false in most computational models, including query complexity. And this kind of suggests that Yau's approach cannot be generalized because it of course, Yaus tells you that it's true if you exchange the for all gamma and the exists mu. If you exchange those quantifiers, then it's true. But this version is actually false. What we show instead is that the following is true: that for all f there exists mu, such that for all gamma, the average case cost against mu of computing f to bias gamma is at least gamma squared r of f. And here r of f is the worst case cost of computing f to bounded error. And the gamma squared is what you would get from amplifying r sub gamma. So if you were to amplify r sub gamma to get like a lower bound on r sub gamma, you would say r sub gamma must be at least gamma squared r of f. So this version where you've already amplified and you get a slightly weaker statement, this version turns out to be true. Okay. And this is still, in a sense, a generalization of Yao's minimax, because you have a single distribution that's hard for all bias levels at once. Okay, so slightly short on time. Briefly, how do you prove Yao's minimax before we consider generalizing it? Yao's minimax, well, you view randomized algorithms as kind of, you know, convex combinations of deterministic algorithms. And, you know, probability distributions are convex combinations of inputs. And Yao's minimax basically is a literal min max equals max min. It's literally saying, you know, minimize algorithm, maximize mu of this function of r and mu, which is the error r makes on mu, is equal to the max over mu min over r of the same error function. This is the Yao's minimax. And note that this error function inside is bilinear. It's linear in r and it's linear in mu, where, you know, we take r and mu to be kind of vectors of probabilities, like these probability vectors, because both r and mu are basically distributions. Okay. And in particular, because this is bilinear, then the min and max are both achieved at a boundary point. So you could really look at it as kind of min r over max x, where x is just a single point. And then you get equal, this is equal to max over mu min over d, where d is a single deterministic algorithm. And this follows from, you know, the fact that when you optimize a linear function over a polytope, then you'll get your optimum would be one of the extreme points, one of the boundary points. Okay, so this is this last statement is exactly the statement we wanted, which says that there is a distribution, the distribution given by the max on the right-hand side. This distribution there is the hard distribution against which average case hardness is as hard as worst case hardness. And the left-hand side basically represents worst case hardness, and the right-hand side represents average case hardness. Okay, and the way we've generalized it is to say that, you know, okay, Yao's minimax, well, what did it do? It used a minimax theorem for bilinear functions, which was introduced by von Neumann, I believe. It's also a special case of LP duality, but it's you know, it maybe for our purposes better to view it as a special case of Sion's minimax, which is just a more general minimax theorem that tells you when you can switch the order of an infinite soup. And Sion says you only require alpha to be semi-continuous and quasi-saddle. Okay. Also, P, the sets over which you're optimizing have to be convex, and one of them must be compact. And, you know, in our case, the compactness will follow from the finite input set. Okay, these are the technical requirements. Let me just skim over this quickly. So using Sion's minimax, here's what we show. You know, and we expect this was known in the literature by somebody somewhere, but it wasn't known to us. What you can do is you can do an inf soup equals soup inf, even for a ratio of bilinear functions, where you have a bilinear function at the top and a bilinear function at the bottom, with a plus, where the plus denotes the maximum with 0. So like, you know, the score of R mu plus means the maximum of 0 end score. So the score could be negative here, and the plus, you know, forces it to be 0 if it were negative. And dividing by 0 gives you infinity. Okay, so with this setting, then the inf sup equals the sup inf, just from science minimax, assuming cost and score are bilinear. Okay, and this is very strange. What's strange to us that you can take minimax. There's a minimax theorem for ratios of bilinear functions. And it even works if cost and score are merely saddle. I won't define saddle, but it's a generalization here of bilinearity. Okay. And so what we would like to do is use this to prove the stronger version of Yao that we wanted. And you know, you can attempt to say that the score at the bottom here should be the bias. And you know, you get something true because the bias is bilinear. But you know, what you get is not very interpretable because the left-hand side is no longer the worst case cost of the randomized algorithm. It's something weird. And you know, what we would like the left-hand side to be would be cost of R of x over bias squared. Because if that were the left-hand side, then we can amplify and turn it into worst case randomized, the randomized cost. So that would turn the left-hand side into R of f, the worst case cost of computing f to bounded error, because amplification costs 1 over bias squared. So I'm running short of time, so I'll just not go into detail here. But if what we had here was cost over bias squared, then the left-hand side would turn out to equal R of f up to constant factors because of amplification. Okay. Unfortunately, we cannot just take score of R mu to equal bias of R mu squared because that's no longer bilinear and it's not saddle and nothing is going to work. Okay, so scoring will save us here. The worst case expected score can be amplified linearly, not quadratically. So when we take score to be the worst case expected score and cost to be some like kind of normal ordinary measure of cost, then we get the following minimax, and the left-hand side does become equal to R of f by amplification. And the right-hand side becomes equal to kind of, well, the right-hand side allows us to conclude that there exists a mu such that for any target score S, the cost of achieving score S against mu is at least omega S times R of f. And converting between scores and biases gives us the same statement, but with a bias squared. Okay, so this basically works in pretty much any model of computation that satisfies both Yao's minimax theorem and amplification. So randomized query complexity, communication complexity, randomized circuits models. We have an improved version of Impagliazzo's hardcore lemma. We have a quantum version of this polynomial degree approximate log rank. So basically this works everywhere. You just need a finite input set. Okay. Okay, we even have a Hellinger interpretation here, which I will, I guess, not get into at this point. Okay. So finally, back to query complexity. This was the composition problem that, you know, the composition question we wanted to address. Is R of f composed G at least R of f times R of G? And what we got is, you know, using this improved minimax theorem, to use as a sufficiently hard distribution for the inner function G, we were able to show R of composed G is at least omega noisy R of f times R of G. We have a characterization of noisy R of f in terms of R of f of something else. Fine, so we have a complete characterization of what noisy R of f is. It's not some completely new measure. Okay, fine. But the key interesting thing here is that this is the strongest composition theorem of its type. So R of f composed G, if R of f composed G is at least M of f times R of G for any measure f M, then we can show that noisy R of f is at least as good as M. So this is, noisy R of f is truly the biggest thing you can put there as a, you know, as something where you say R of f composed G is at least something of f times R of G. Noisy R of f is the largest such thing. also, we show that R of F composed G can be smaller than R of F times R of G. So the original composition conjecture is actually false. So the statement R of F composed G is at least R of F times R of G is just plain false. And the best you can do instead is to say R of F composed G is at least noisy R of F times R of G. And this is guaranteed to be the best you could possibly do. Okay, so just finally an open problem slide. The open problems are, what are other applications of forecasting algorithms are there? We strongly feel like there should be more of them in the case where you care about fine-grained analysis of small batch randomized algorithms, but this is a bit of an unusual setting. Another question is, okay, so we only really analyze this one magic squaring rule, but some of the other squaring rules are very elegant mathematically, and maybe they should have some application to complexity theory as well. And finally, are there other applications of the new minimax theorem? We used it to get a new result for joint computation of query complexity in query complexity, but what about joint computation in other models? Communication complexity, circuit models. Can we say anything new using this new tool? Okay, thanks.
Okay, thank you very much, Shalev. Okay, if anyone has questions, please ask.
Hi, I have a question.
Yep.
The gap majority
Mm-hmm.
in your in the bound there, can you explain kind of why that comes into play? Why is that important?
Yeah. So, okay. So, all right. You're computing. Let's see if this F composed G thing in this diagram here on the right that I'm looking at. So you're trying to compute F composed G, and the question is, can you cheat and not just run an algorithm for F and compose it with an algorithm for G? And the answer is yes. Sometimes you can cheat. Why? What information do you have access to here that you don't when you're just computing F or G? And the answer is, what you can do here is you can compute G. Imagine computing one copy of G to very small bias. Compute one copy of G just a little bit and just get an idea of whether it's likely to be 0 or likely to be 1. And then stop computing it. Come back to it later. Stop computing it for now and use it to guide your other decisions of what to query next on the F level. So this is sort of saying, all right, this is effectively saying, what an algorithm for F has access to here is it has access to kind of noisy oracles for its inputs, where the noisy oracle, right, where you're computing G just a little bit, and it's much cheaper than computing it a lot. So noisy R of F is the cost of computing F in this noisy oracle model, where it's cheaper to get a little bit of, information about the input bit, but expensive to get a clean query of the input bit. And you can implement this kind of noisy oracle with a gap majority gadget. So you can put the inner function to be this one G equals gap majority, and it will implement this tricky setting where by making few queries you can get a bit of an idea, and by making more queries you get more of an idea of what the value of G of the input will be. So that kind of implements this gap majority setting. Yeah, I'll just leave this up here. Yeah, any other questions?
So Shalev, so in terms of the scoring rule, so why do you require the scoring rule only to depend on Q as opposed to depend on like F and Q or something? Because usually, I don't know, people would use like relative entropy as good measures, but it is not of the form of the scoring rule that you have, right? Like yours only depend on like S only depends on the response as opposed to the response with respect to the probability.
Yeah, so I guess we're in a setting where we don't know the true probability of the event happening. So we us as evaluators, we don't have access to the true probability it will rain. It's not even clear that there is a true probability it will rain, philosophically speaking. All we know is whether it rained or not, and we would like to give a reward based on that. And kind of why this is the right thing to do for in the forecasting algorithm setting, that I'm less sure, because I mean there the situation is even stranger, because there's no prior distribution at all. Like there is no distribution that you're trying to get right, like that you're trying to match some target distribution. There is no underlying prior distribution at all. It's not even clear why scoring it by a proper scoring rule in a way which incentivizes a Bayesian to give her true subjective probability, why that should be relevant or why that should come up at all. It just happened to come up, and to feel like the right thing once it comes up. But yeah, I mean, I think I think if you try to do a relative entropy here, the question will be relative to what? What is the underlying distribution?
I see. There's another question from Akshay. When is the composition conjecture false?
When is it false? Right.
Yeah.
So so the so the example is well, I mean, it's not the cleanest example, but okay, it's not so bad. G will just be the gap majority function that I have here on the slide. Gamma gen, that will be G. And in fact, you can always assume that that's the inner function. So on the other hand, f will be a function where, let's see, so roughly speaking, f will be a sort of, so first of all, f will be a properties problem. So I guess I'm cheating a little bit here. So f is not a total Boolean function, and also I guess G is not either. They both have promises on their allowed inputs, and f will kind of treat its first log n bits of the input as a special string, and the goal of f is to so the goal of f is to first approximate that string. So find a string that is a bit better than agrees with this first log n bits on a bit more than half the bits. So it agrees on half the bits plus root of the bits, just out of the first k equals log n bits. So your first goal is to basically get a string for the first k that approximates the real first k bits. That's goal number one. And then goal number two is you have a long array of length 2 to the k, and you will look up this string in the array, and the promise will be that kind of if you query an index where which really matched, which really was close to the first k bits, if you query such an index, you will see the right answer to the function. You'll see like 1 or minus 1, 2. And then if you query any other position, you will see a junk. You will see like let's say a 2, or like you will see something that doesn't make any sense and doesn't give you any information about the value of the function. So f is a function of that sort, which effectively forces you to get an approximation of a string where there is an input string x, and you want to find a string y which agrees with x on a bit more than half the bits. And this task turns out to be easier to do if you have access to noisy oracles for the bits, where each noisy oracle call is really cheap. Then you can just query all the bits with this noise, and kind of you get a really, really cheap estimate for this kind of cheap way of finding a string y that's close to x, that's a little bit correlated with x. But if you only have access to kind of expensive clean queries, then you need to make the number of clean queries you need to make depends on this distance you want between y and x, but it turns out to be more expensive. Yeah, it would be easier if I had a board here, I guess. I don't know how much I was able to convey that over just by talking.
I have another question.
Yeah.
From what you said at the beginning, it sounded like most of the lower bounds for these kind of compositions are on R of F times some other complexity measure of G. So
Right.
from that, it seems like it would be more desirable to get a bound here that's like R of F times M of G, where M is something else. Does this technique, could it be used for that sort of lower bound?
Yeah, so that's a great question. So we don't have a new lower bound of this sort. So you know, the only thing we were able to do with our new technique, the only kind of place where we could beat the you know, previous literature was in the dependence on F, basically because we have a better hard distribution for G that gives us better way to you know, to it kind of allows us to fix the complexity of the inner function G to really be R of G, and then we analyze F and we get this other measure noisy R of F. So yeah, so it's a great question, and I don't know the best. We don't know. We don't have a measure which is known to be the best possible for G. So we don't know. We don't have a measure that's known to be the best that you can do of the form R of F composed G is at least R of F times that measure of G. We do have a measure which is, you know, the best of the art, the state of the art currently. That's not ours. That's previous work by a variety of authors, and you know, their measure, they call it conflict complexity, and it's at least square root of R of G. You know, and for the gap majority function, it will be equal to root n instead of n. So that would be this gap majority thing is a kind of an example which maximally separates conflict complexity from randomized query complexity. But yeah, there is no guarantee there that conflict complexity is the best possible.
Okay, great. Any other questions? Okay, if not, let's thank Shalev again for the great talk. And yeah, thanks a lot, Shalev. Let me stop recording here.
Thanks, Shalev. Nice, yeah.